Alright, hello, welcome. Welcome to lesson 4.6 part 2, where we continue our exploration of graphs of trig functions. We're going to be looking at the graphs of secant, cosecant, and cotangent in this video. So let's go ahead and list the learning objectives. So we're going to graph those three functions. We're going to use their graphs to solve some problems and determine their domain and range for each function. The second part, the second learning objective, we will accomplish through the worksheets. So you guys will be practicing finding when the secant is equal to some value and seeing how the graph relates to that problem. Okay? So without further ado, we're going to focus on 1 and 3 in this video, and 2 you're going to accomplish on your own in the class. Alright, so table of values. We're going to start off by looking at, cosine, sine, and tangent are kind of the root functions of secant, cosecant, and cotangent. So recall the table that we created for cosine and sine and tangent, and when we're computing secant values or cosecant or cotangent, we're just taking the answers from the cosine, from the answers from here, and sine from cosine, sine, and tangent, taking their reciprocals, okay? And those will give us the values for the other functions, okay? And remember, reciprocal means reciprocal means 1 divided by whatever that number is. So taking the reciprocal is flipping the fraction, doing 1 divided by that number. Okay, so here's a big old table of values for cosine. The one on the left two columns you already have. So that's what we built together in the last lesson. Based off thinking about the unit circle and then finding the x-coordinate for those points on the unit circle because it's the cosine. For secant's table of values, we're just taking the reciprocal of each of the answers to cosine. So for example, if I want to compute secant of pi over 6, I'm going to use a different color, we're going to use red. I want to compute secant of pi over 6. I first find the cosine of pi over 6, square root 3 over 2, and then I take its reciprocal. So the secant of pi over 6, 1 over square root 3 over 2. And so when you take the reciprocal of a fraction, that means flip it, the numerator and denominator. So if you take the reciprocal of the fraction a over b, that means you get b over a. So it flips the fraction. And so we get 2 over square root 3. And you can rationalize that if you so choose and gets you 2 root 3 over 3. But more importantly, I want to know what that number is approximately. And it's about 1.15. So the secant of pi over 6 is about 1.15. And then likewise for pi over 4, we take the secant, we take the cosine of pi over 4, and that gets us square root 2 over 2. When we take its reciprocal here, 1 over square root 2 over 2, that gives us 2 divided by the square root of 2, which again you can rationalize and you end up getting square root 2 as the answer, which again for plotting purposes is about 1.4. Going on, pi over 3 is a half. Taking this reciprocal of 1/2 gives us 2. And when the cosine, when our angle is pi over 2, the cosine is 0. And when we take the reciprocal of 0, we get undefined. 1 over 0 is undefined. And so that actually ends up not being, ends up being an asymptote. This is going to give us a vertical asymptote. So I'll just mark, yeah, it's a vertical asymptote. And so forth. We can keep computing values as we go. The secant of 2 pi over 3 is negative 2. The secant of 3 pi over 4 is negative 1.4. Secant of 5 pi over 6 is negative 1.15. And the secant of pi is negative 1. So we're going to plot each of these theta, secant theta pairs on the graph. So starting off with 0, 1. There's 0, 1. And then we plug pi over 4 in. So I'm going to find half of pi is right there. So pi over 4 is going to be right, let's see, 1, 2, 3, 4, 5, 6. So 3 boxes in. That's pi over 4 right there. So pi over 4, I get about 1.4, sorry, I missed pi over 6. Pi over 6, that's about 1.15. So that's about here, somewhere around there. And then pi over 4 is right here, and that's 1.4. So that's about at pi over 3 we get 2. Okay, getting steeper now. Get 2. Pi over 2 is undefined, so I'm going to go ahead and draw this vertical asymptote. I know it's going to be a vertical asymptote because I know that our numbers are increasing when we get close to pi over 2, and so the cosines are getting closer to 0. 1 over a number getting close to 0 is blowing up. It's getting big. You know, for example, 1 divided by 0.01 is 100. Okay, so when that denominator gets small, the numerator stays 1 the whole time. You end up getting a larger and larger answer as a result. So our graph for secant is going to look something like this. Go up to infinity like that. Okay, and then carrying on, as we move past pi over 2, at 2/3 we have -2. At pi we have -1, so I'm going to plot -1. At 4/3 we're also going to have -2. We get another vertical asymptote at 3 pi over 2. That's the other time the cosine is 0. So there's another vertical asymptote. And filling in kind of what happens in between, it's going to do something like this. Infinity, go off to -infinity, and we rinse and repeat. Make sure I get through that point right there. So let's go ahead and, okay. So there's the graph of secant based off of the graph of cosine. Now, what I want to do is I want to sketch cosine on this as well. And I want to show you a kind of an alternate way to do the graph of secant based off of the graph of cosine. So kind of using cosine's graph as a guide instead of computing these tables of values the way that we are doing for secant. So this is tedious to create this table every time. So instead, I'm going to just really know cosine's graph. So if I were to graph cosine, I'm going to do it in blue. I know 0, 1 is a point. I know pi -1 is a point. I know that pi over 2 is 0, and 3 pi over 2 is 0, and 2 pi 1. And so here's my graph for cosine. Here's the nice smooth cosine graph. So I want you to look at how the graph of secant matches with the graph of cosine, how those guys are related to each other. Whenever cosine is 1, secant is 1 as well, because 1 divided by itself is 1. Whenever cosine is -1, for example at pi, the secant is -1 as well, because 1 divided by -1 is also -1. Whenever the cosine is 0, then the secant is undefined, because 1 over 0 is undefined. So at pi over 2 and 3 pi over 2, we're going to get vertical asymptotes. Okay? So the graph of secant can be drawn or sketched in based off of the graph of cosine. So you could start instead by graphing cosine, finding when it's 1, -1, and when it's 0, and using that as a guide. And in fact, that's what we're going to do when we do the graph of sine. So that's coming up next. All right. So here's the faster method to graph in cosecant based off of, or to graph in cosecant based off of those facts about what happens when you do 1 over various numbers, right? So whenever sine is 0, we're going to get a vertical asymptote. Whenever sine is 1, we're going to get 1. And when it's -1, we're going to get -1. Okay? So we'll graph sine first. We're going to start off with the graph of sine. So I remember sine of 0 is 0, sine of 2 pi is 0, sine of pi is 0. At pi over 2, it's 1, and at 3 pi over 2, it's -1. So here's a sketch of sine's graph. The guide, this isn't the graph of cosecant, this is a guiding graph. Okay, so there's the graph of sine of x. Now we're going to go ahead and graph cosecant based on this graph. Remember I said whenever the sine is positive or -1, the cosecant is going to be positive or -1. So, for example, at pi over 2, sine is 1, so cosecant is 1. At 3 pi over 2, sine is -1, so the cosecant is -1. When sine is 0, cosecant will have a vertical asymptote. So there's a vertical asymptote at 0, and at pi, and at 2 pi. And then we're going to sketch the curve in between, right? So we know that it's going to go up to infinity as we approach these vertical asymptotes and down to -infinity, the vertical asymptotes over here. So if we want to get more specific about these values, we can, but this is sufficient. I know I'll just add this one in here. Whenever sine is 1/2, cosecant's 2. So we'll plot those as well. So pi over 6, 2. That's right here. Pi over 6. And this guy right here, which is 5 pi over 6. Those are actually nice values to get in there as well. Let's go ahead and do that. 5 pi over 6. That's at 2 right here. And then at 7 pi over 6, which is here, and at 11 pi over 6. We're going to get those guys as well. 11 pi. So let's go ahead and fit those ones in. We'll make our graphs a little prettier. So here we go. At 7 pi over 6, it's -2. At 11 pi over 6, it's -2 as well. So we're going to just get these guys going like that. Fantastic. There's the graph of cosecant. Okay. So for cosecant, cosecant's domain. I forgot to say the domain and range of secant. We'll come back to that. The cosecant, the domain of this function, it would appear is every x that's not a multiple of pi. So whenever x is a multiple of pi, the sine is 0, and then the cosecant's undefined because we're trying to do 1 over 0. So at 0 it's undefined, at pi it's undefined, at 2 pi it's undefined, and etc. so forth. So it's everything except for multiples of pi. So n is an integer. N is any, and our range, ooh, here's a tricky one. If we were to look at the range of these graphs, we're scanning it from bottom up. So we can see we have graph down at -infinity, and we come up, and we have graph all the way up to -1. There is a gap. We don't, we draw horizontal lines. We don't actually hit cosecant's graph between -1 and 1. And the reason why we're not going to get those values in between is because then the sine would have to be like 3 or 5 to have its reciprocal be between -1 and 1. And then we know that doesn't happen, right? So the range of the cosecant function is determined by the range of the sine function. We're never going to get sines of 5 or 10 or so forth. And so we're never going to get cosecants that are smaller than 1 or in between -1 and 1. So there's no graph in between those two y values. So our range is from -infinity to -1 inclusive. We hit -1 right there. Union 1 to infinity. from 1 up. So we have from negative infinity to negative 1, nothing, and then from 1 to infinity. So we have a weird range for the cosecant graph. Backtracking to secant's graph, let's just list this out. Our domain is the only thing different. The range is the same. Range is the same as cosecant. Okay? The domain is a little different. We have these, again, vertical asymptotes. They're just happening at different times. They're happening whenever cosine is 0 now. And that happens at pi over 2. This is pi over 2. And 3 pi over 2. And then you can just keep adding multiples of pi on to one of these numbers and you'll get another vertical asymptote. So any multiple of pi added to pi over 2 is going to get you another vertical asymptote. So x cannot be pi over 2 plus a multiple of pi. That's our domain for the secant function. Those are x's, those are angles, where the cosine is 0. That's all of them. Okay? Okay, we're going to build cotangent lastly, and we're going to start with the graph of tan. We're going to take its reciprocal, and from that build the graph of cotangent. Okay? We could also graph cosine and sine and look at that ratio to come up with the graph of cotangent. Either way works. Okay, so we'll start off by sketching the graph of tangent. So I've been using blue. We're going to use blue for the graph of tangent. Tangent is 0 at 0, 0 at pi, 0 at 2 pi. Has these vertical asymptotes at pi over 2 and 3 pi over 2. It's one that has the same domain as secant. And then we know at pi over 4, which is right here, it's 1. I'm going to plot that point. That's an important point. So it does something like at 3 pi over 4 right here, it's negative 1. That's it's going to go down. It's going to hit the x-axis at pi. At 5 pi over 4, it's positive 1. 5 pi over 4. At, let's see, 7 pi over 4, it's negative 1. 7 pi over 4 is negative 1. So it's going to do something like this. Okay, so that's a graph of tangent, sorry. So this is tan x. Now we're going to graph cotangent. So remember, when we take reciprocals, we're taking reciprocals of the y values. So we're going to look at a point, look at its y, take its reciprocal, and that's going to be on the graph of cotangent. So whenever the tangent is 1, the cotangent's going to be 1 again. Whenever the tangent's negative 1, the cotangent will be negative 1 as well. Let's use purple for cotangent. I like purple. It's a great color. So when the tangent's 0, cotangent is undefined. It's going to have the vertical asymptote. And then the opposite will be true. Whenever tan has a vertical asymptote, then cotangent is 0. Okay, so we're going to have these zeros for cotangent on the vertical asymptotes of tangent. So we'll start with that. We've got vertical asymptotes at 0 for cotangent's graph. So there's one. Here's another one. Here's another one. 0, pi, 2 pi. These are all vertical asymptotes. And then I said that whenever tangent has a vertical asymptote, that means cosine is 0 and sine is 1. That means cotangent will be 0. So we've got a 0 here and a 0 here. Okay, and then we have the other points. When the tangent is 1, cotangent is 1. Fantastic, so we'll go through there. When the tangent is negative 1, the cotangent's negative 1 as well, so we're going to go through there. And then we'll just go ahead and sketch this curve in all nice towards the asymptotes. There and there. up to infinity. Fantastic. So that's the graph of cotangent of x based off of the graph of tangent. Whenever the tangent is 1 or -1, its reciprocal is the same. And whenever the tangent is undefined, a vertical asymptote, the cotangent is 0. Whenever the tangent is 0, the cotangent is undefined, it has a vertical asymptote, and so forth. Okay? So you can build these graphs based off of your understanding of what does it mean to take the reciprocal of a number. Okay? Okay, so there's our graphs. The next thing we're going to do in this unit is going to be about sinusoidal modeling. So that's going to be taking our curves, taking our functions, and fitting it to some real-world data that has this repetitive behavior. So cosine and sine are functions that repeat over and over and over. And so there's many things in the real world that have a repeating pattern to them that we can use as inspiration and try to fit a sine or cosine to that data. And all it will be is transformations on these functions, but we're going to introduce some different terminology because of how common it is to transform functions that repeat into sinusoids. These are called sinusoids, sine and cosine. And so there's going to be some different terms we'll use, but they're the same, you know, vertical shift, horizontal shift, vertical stretch, horizontal stretch. All of those will be, but just with different words for these functions. Okay? So that's what we're going to get into when we come back in the next lesson. Will be about sinusoidal modeling. So until then, I'll see you guys next time.